In this module, we will review the basic relationships between events. In particular, we will go over concepts regarding complement, intersection, union, and mutually exclusive. It is useful to illustrate the relationships between events through a Venn diagram. A Venn diagram shows the logical relations between a collection of sets. You can think of a set as an event. Let us draw a Venn diagram using the following example. In the experiment of tossing a coin twice, there are 4 possible outcomes. We may get 2 heads in a row, or get 2 tails in a row, or get 1 head, then 1 tail, or get 1 tail, then 1 head. These 4 outcomes form the sample space. We usually use a square to represent the sample space. If we define an event A as getting at least 1 tail from this experiment, then we can use a circle that includes tail-head, head-tail, and tail-tail to represent event A. Similarly, if the experiment is to roll a die, the sample space contains the 6 numbers. Suppose we define event B as getting an odd number, then we can also use a circle to illustrate that event. Next, I'm going to utilize Venn diagrams to introduce concepts of complement, intersection, union, and mutually exclusive. Let's start with the complement of an event. An event's complement contains all sample points that do not belong to the event. We use the superscript C to denote complement. In a Venn diagram, we can draw an event, say event A, then every sample point that is outside of event A's circle belongs to A complement. Let's define an experiment as randomly picking 1 student who is taking this class, and know the student's age. Define event A as less than 21 years old. Then, what is event A complement? In this case, we know that students who are not less than 21 years old belongs to A complement. Therefore, event A complement is getting a student who is greater than or equal to 21 years old. If you recall the phone calls example from the previous module, if we define event A to be getting at least 1 call during lunchtime, then A complement is getting 0 call. Next, we will look at the intersection of 2 events. The intersection of 2 events contains sample points that belong to both events. Mathematically, we use an upside-down U to denote intersection. In this Venn diagram, we have 1 circle that represents event A. We have another circle that represents event B. The 2 events overlapping part is the intersection of the 2 events. To apply this concept, let's look at an experiment of randomly drawing a poker card from a deck. We define event A to be getting an ace, and event B to be getting a black card. Then, there are 2 cards belonging to both events. We said that these 2 cards belonging to A intersect B. Note that A intersect B is the same as B intersect A. In this example, the probability of A intersect B is 2 over 52, which is approximately 0.0385. Let's look at one more example. In an experiment of rolling a fair die once and know the number, let event A be greater than or equal to 3. Let event B be even number. What is probability of A intersect B? We know that there are 6 possible outcomes that are equally likely. Event A contains 3, 4, 5, and 6. Event B contains 2, 4, and 6. Therefore, event A intersect B contains 4 and 6. The probability of A intersect B is 2 over 6, or 1/3. Now, we are ready for the concept of union. Suppose we have event A and event B. The two events' union includes sample points that belong to either event A or event B, or both. We use a U-shaped notation to denote union. Let's use the same poker card example. Define the experiment as randomly drawing a card from a deck. Let event A be getting an S. Let event B be getting a black card. Then A union B contains any sample points in event A or event B, which contains the 2 red ace cards and 26 black cards. The probability of A union B is 28 over 52, which is about 0.5385. Now, let's look at one more example. Let the experiment be rolling a fair die once. Let event A be getting a number that is greater than or equal to 3. Let event B be getting an even number. Then event A contains 3, 4, 5, and 6. Event B contains 2, 4, and 6. In other words, event A union B contains sample points that either belongs to A or B or both. Therefore, event A union B contains 2, 3, 4, 5, and 6. A total of 5 outcomes. Then it is straightforward to see that the probability of A union B is 5 over 6. Now, we move to the next concept, mutually exclusive events. If two events are said to be mutually exclusive, then they cannot happen at the same time. In other words, the two events have no sample points in common, or, if we put differently, the two events have no intersection. We can see that in this Venn diagram, event A and event B are well separated. They have no overlapping and they are mutually exclusive. Let's look at the poker card drawing example again. Let event A be getting a heart card. Let event B be getting a spade card. The two events have nothing in common. Therefore, event A and event B are mutually exclusive. It is also straightforward to infer from the Venn diagram that when event A and B are mutually exclusive, probability of A intersect B is 0, and probability of A union B is probability of A plus probability of B. Let's look at one more example. Let the experiment be rolling a fair die once. Event A be getting an odd number, and event B be getting an even number. Then, we can see that event A and B have no elements in common, and they are mutually exclusive. The probability of A intersect B is 0 because there is no sample point that belongs to both events at the same time. The probability of A union B is 1 because A union B forms the sample space. Finally, I'm going to let you work on an example on your own.